Hey, what's going on, guys? Kings here. In this video we're going to be implementing iterative deepening, a technique allowing us to do, well, at least two things. So first is to handle timings. So let's say that your time is up and you need to return the best move you have at this moment. So that's one of the applications. So let's say you're searching like to depth 1, depth 2, depth 3 and so on, and then you're kind of out of time. So instead of completing the search to say depth 7, you just return the search from depth 6, the previous search, the previous depth's best move that you already have. And another idea is to apply the technique of sorting principal variation moves that you are retrieving from the principal variation lines as they appear during this iterative deepening search. But before that, I just want to add some little clarifications into the source code, and also to make sure that our plies are not gonna get exhausted during the search. So just to avoid overflows of this killer moves, history moves, and the principal variation length and table arrays. So and also one more little thing. So I want to define the maximal ply that we can reach. Let's say maximal number of maximal ply that we can reach within a search. So I just want to define a variable called maxPly like this, and it would be equal to 64. So now I will make so everywhere we're dealing with our plies, I just want to use this constant of maxPly. Sorry for doing this lowercase. I know that in C programming language you would do this in uppercases, but I really like this Python style, so just that's the reason I'm doing this lowercase for naming the constants. Okay, so here we're not changing this because it's not the ply, it's the square. It's completely different, so just to give you an idea. And also here where we're initializing the PV table length, I just want to give you an idea that this is the ply. Sorry, I didn't do this the previous video, just forgot that. So we can apply maximal depth here as well, and PV table is indexed by ply for both dimensions, the first and the second index. And here we can also use this maxPly. And let me actually open the terminal, compile and run the code, and then we'll proceed. So make debug, and if it makes, I want to run the BBC binary executable. Okay, let's drop back to the debugging mode here. So okay, and just wanna see the search working. Okay, so this is the number of our nodes from the previous part. By the way, guys, for those of you who has been watching the previous video attentively, you probably could see that when I did add the feature of adding the feature of collecting of storing history moves only in those cases when we're dealing with the non-captures or the quiet moves, I said like that the number of nodes that we have was decreased, but actually it was slightly increased. And I just want to say, well, obviously that was a mistake what I said in that video, but I just want to say that if we go to the depth of 6, it would be clearly seen like how that is going to get decreased. So I don't really want to spend time on this, but you can just check this. Just switch the depth to 6, and you'll see that the nodes would get decreased if you get rid of that. So let me just show you this. Okay, history moves. So here, well, I just want to let's better. I will show you this. So we just get rid of this stuff. It would get a less number, which yeah. So I said that this number is actually less than this one, and this is obviously not true. But if we just go to the depth of 6, save and then go to history back. Okay, and now let's run the search again. So at this moment we're storing moves, not the quiet moves, but every time, even for the captures. And in this case we're getting this number of nodes, so 845109. And now if we actually do store history moves only on quiet moves, so not doing this on capture moves, then at the very end, so 5, we have 845109, 845015. Well, it's not significant. Now I can say this for sure. It's not significant decrease, but just as a proof of concept. And conceptually, it's more like the right way of doing this, because we're sorting captures separately from the quiet moves. So that's it. So, well, obviously it's not really that essential if you do use this line or do not use this line, but I just wanted to point your attention at this point, at right over in here. Okay, so well, probably we can stay at the depth of 6 at the moment, because it would allow you to show the more significant difference on saving the nodes when we would be sorting the principal variation moves. Okay, but before anything else, before I forget to do this one little important thing here within the Nigimax search, just after we dealing with our recursive escape condition, we want to drop the search in case if we exhaust the maximal depth, the maximal ply constant. So is this still here? Yeah. So, well, let me just first implement this and then I'll give a commentary. So we just say if ply is greater than max ply minus 1, this means that we are too deep, hence there's an overflow of arrays relying on a max ply constant. And so if we don't do this, your engine might eventually crash. That's the reason. Very simple. So in this case, I just want to say I'm not going to be returning quiescence. In this case, I just want to return evaluate straight ahead. Most likely, we're not ever going to reach this position. Just evaluate position. But just to make sure everything is going to be fine, we're using this code. So to make sure that there won't be any overflows of those array relying on the max ply constant. So let's compile and run this again, and obviously nothing should really change here. Okay, yeah, still the same number of nodes, the same PV. Okay, yeah. So starting from this point in particular, we can already go for our iterative deepening. So okay, it would be right over in here. And again, like a few lines of code before we go to iterative deepening, we want to clear for search, clear all the clear helper arrays, helper data structures for search, like this. So the idea that we want to be calling this search position within the UCI loop many times, and if we don't clear our killer moves, history moves, principal variation table, and principal variation length array, there would be lots of garbage there, which would be slowing down the process of finding the moves significantly. And in my earlier engines, I didn't do that, and I had no idea like why at the middle game it started to make moves very slowly, slow as hell basically. And then I realized that I just forgot to clear this stuff. So I would be using the memset function here. So first let's clear the killer moves. So killer moves, and fill up them with the zeros, and the size of killer moves like this. Okay, so the next then would be to do the same but with the history moves. History moves, okay. And also with the PV table. Okay, and also with PV length. Well, actually, in TCP in particular, PV length is not getting initialized for some reason. But as far as this won't really affect the performance, I still want. This is just done once. We call the search position. That doesn't take time really. So just to make sure that would be that would be clear as well. I just want to clear this PV length as well. So let's make sure it still compiles and run. Okay. I feel like something wrong there. Okay. PV length. Okay. Okay, and also in order to have a valid number of nodes, we want to clear the nodes as well. So reset nodes counter. So nodes would be equal to 0 like this. Okay, and also I would like to go for a comparison between this non-iterative deepening and iterative deepening with certain PV moves versions of the search position function. So I would leave this code just for a while, and then I just make a copy, implement the iterative deepening. Well, okay, so let me just do this stuff, and then I will explain what's going on along the way. So now I just want to copy this code, and first, well, let's just paste this. So the idea is that we would be searching this position twice at the moment. Redefinition of score. Okay, this is a little bit of an issue. So let's make the score variable as defined the score variable before. Okay. So it's let's make it the verb first. So define best score variable. So integer score. Well, we could have used this best score, but doesn't really matter that much. So it would be equal to 0. Okay, and now it should run two absolutely the same searches, and if they are really absolutely the same, they just will have the same number of nodes being traversed. So this is just what I wanted to show you guys. Now, just to give you an idea what happens if we don't do this really. So, well, let's say if we forget to update the nodes, so the number of nodes would be twice more, because we just keep adding those nodes again and again, even though the speed would be the same, but the amount of nodes would be twice bigger. It's not because it searched more nodes, it's just because we forgot to reset the counter. And I'm emphasizing all these things because nobody really explained this to me, and I was learning this on my own mistakes, so I just want you guys to avoid these disasters. Okay, so now the nodes would be the same, but instead, if I just forget to clear my search data structures, the results already would be a bit different. And it doesn't obviously mean that they would be worse. At some point they might be even better, but the idea that they are not the same, which is wrong. That, yeah, well, actually, Actually here we have a better results, but that's just because we're searching the same position. But if we just go and search for a different position with the garbage from the previous position, it would really get wrong, and that's a complete disaster. So don't get tempted with this seemingly my god, I forgot the word with this seemingly reduced number of nodes. So we always have to actually clear all this stuff here. Okay, so finally now we can go to our iterative deepening, and it would start right over in here, just right below the clear of helper data structures for search. So here I just want to say iterative deepening, and now the idea is very simple. So we just look over the depth that we are retrieving within our search. So I can simply say like for integer current depth equals to 1, not 0, it's important, it equals to 1. And now current depth is less than depth, less equals than depth, again it's very important. And finally current depth plus plus. And now just want to enclose the below code up to print in the principal variation, but not the best move, because we want to print the best move at the very end. That's important. Okay, and here we want to search not for a depth, but for the current depth in deepening ply by ply. So it would now get clear when I show you the output. And yeah, and also we're printing the principal variation, and here so we're printing the current depth, and also we're searching with the current depth. Okay, and obviously now the number of nodes eventually traverse to get this sort of a PV line, or the depth of 6 would be greater than this value. But don't get confused by this, because this is something that was confusing me really a lot. I just want to explain you the idea behind why this is happening. So, well, it seems like this number is much greater than this one, and this is actually true, but the idea is that all these previously traversed nodes are getting added to this value. So that's kind of the idea. So during the game itself, so when we will actually be, when we will actually be using this in a ready-made engine, this is the exact way to calculate the nodes. Well, at least according to the implementations that I've seen in other engines, they usually do not reset the nodes within the iterative deepening search. Well, it might be a good idea. Well, just what I want to show you guys. So if here at some point we just say like nodes equal to 0, then okay, sorry, just my cats are fighting around. Okay, then okay guys, just hold on a sec. Again, I'm so sorry guys, just was distracted. My cats were killing each other. Okay, so let me just run the search again. Okay, so I just want to demonstrate that if we would reset the nodes every time the depth is increasing here, then we'll clearly see that eventual depth, that the eventual number of traversed nodes would actually be less compared to the depth, compared to if we go to the same depth just straight ahead. So this just shows you like why people saying the iterative deepening is actually faster compared to this straight away stuff. Well, it's not really faster. I mean, it's like because we're initializing all those history and killer moves data structures the moves are getting ordered better during the iterative deepening, and eventually we have less nodes taken when we're hitting the same depth here and here. So just to give you an idea. Okay, so anyway, I just wanted to show you this. Well, obviously later on I won't be resetting the nodes here within the iterative deepening, but for now I just want to keep it in order to show this difference. And also when we will apply the principal variation move sorting to our chess engine, this difference would be even more significant. And when that is clear, I will later just get rid of this node resetting here, and also get rid of this code duplicating the search for the comparison. Okay guys, so this seems like it for this video, and in the next one we're gonna be writing some code in order to sort our principal variation moves within the search to reduce the number of traverse nodes even more. Okay guys, so this is it from my side. I hope you learned something interesting out of this tutorial. Hope to see you in the next videos. Until that time, and take care.